Hi everyone, I am Arjit Manna from Electronics and Communication Engineering Department, second year. Today I will be presenting on modulation techniques, an essential concept in analog and digital communication. Modulation plays a crucial role in transmitting signals efficiently over long distances with minimal distortion and interference. Through this presentation, we will explore different types of modulation, their applications, and emerging trends. Let's begin. This presentation is structured as follows. First, we will introduce modulation and its significance. Then, we will explore different types of modulation techniques, including amplitude modulation, frequency modulation, and phase modulation. We will also discuss the necessity of modulation, its applications in various fields, and the challenges and future trends in modulation techniques. Introduction to modulation. Modulation is a key process in communication that allows signals to be transmitted efficiently over a medium. By varying a high-frequency carrier signal based on the original message signal, modulation ensures that communication can occur over long distances while minimizing distortion and interference. Without modulation, direct transmission of low-frequency signals would be impractical due to attenuation and noise. Various of modulation exist, each with unique advantages and applications in broadcasting, and telecommunications, satellite communications, and more. Now I will discuss types of modulation. There are mainly two types of modulation: analog modulation and digital modulation. Then there are three primary types of modulation: uh, analog modulation, amplitude modulation, frequency modulation, and phase modulation. Uh, Amplitude modulation varies the amplitude of the carrier wave while keeping frequency constant, and frequency modulation changes the frequency of the carrier in response to the message signal. Uh, phase, sig- phase, uh, Phase modulation alters the phase of the carrier waves. Each technique has distinct characteristics, advantages, and use cases, which we will explore in the next slides. Now I will discuss amplitude modulation. Amplitude modulation is a technique in which the amplitude of the carrier wave varies in proportion to the message signal, while its frequency remains unchanged. It is widely used in radio broadcasting and aviation communication. The downside of AM is its susceptibility to noise and signal fading. Next, we will explore different types of uh, amplitude modulation. So there are several types of amplitude modulation. Number one is double sideband suppressed carrier, DSBSC. In this uh, modulation, in this frequency spectrum, both upper and lower sidebands are transmitted, but the carrier is suppressed to improve efficiency. Number two is single sideband, SSB. Amplification of single sideband refers to the transmission of only one sideband. It means only one sideband is transmitted, reducing bandwidth usage and power consumption. So it has a sideband on either the top or lower half. Number three is vestigial sideband, VSB. Uh, in this sideband, a portion of one sideband is transmitted, commonly used in TV broadcasting to balance efficiency and quality. Now I will discuss frequency modulation. Frequency modulation changes the frequency of the carrier wave in proportion to the message signal. So, frequency modulation provides better noise immunity compared to amplitude modulation, making it ideal for high quality audio transmission. It is widely used in frequency modulation, radio broadcasting, and communication systems. Next, we will see different types of frequency modulation. FM can be classified into narrowband FM. In this FM, used in two-way communication like police radios and walkie-talkies, it requires less bandwidth. Next, wideband FM, used in FM broadcasting, providing better sound quality but requiring more bandwidth. Application of FM include FM radio, TV audio transmission, satellite communication, and radar systems. Now I will discuss phase modulation. Phase modulation is an analog modulation technique where the phase of the carrier signal is varied according to the message signal. It is closely related to FM, as phase variations lead to frequency changes. Phase modulation is commonly used in digital communication systems, including Wi-Fi, Bluetooth, and 4G or 5G networks, optical fiber communication, satellite communication, and more. Now I will discuss need for modulation. Why do we need modulation? Number one, prevents interference, means avoids signal mixing. Modulation shifts signals to different frequency bands for avoiding overlap. Number two, increases transmission distance. Low frequency signals experience high attenuation, while modulated signals can travel longer distances. Number three, efficient antenna design. Without modulation, antennas would need to be impractically large. Number four is noise reduction. High frequency modulated signals are more resistant to noise. Number five is enables multiplexing. Modulation allows multiple signals to be transmitted over the same channel. Number six is facilitates long distance communication, essential for radio, TV, and satellite communication. So now I will discuss applications of modulation techniques. Modulation is used across various industries. In broadcasting, AM is used in radio broadcasting uh, for long range transmission. FM provides high quality sound, and VSB is used in TV transmission. In telecommunication, modulation techniques enable mobile communication, internet connectivity, and fiber optic transmission. In radar system, frequency modulation and phase modulation are used in radar systems for aircraft navigation, weather monitoring, and military applications. In satellite communication, ensures efficient data transmission for TV, GPS, and high-speed internet services. Now we will see what are the challenges and future trends in modulation techniques. Modulation techniques face several challenges. Number one is noise interference. And analog signals are highly susceptible to noise and atmospheric disturbances. Number two is bandwidth limitations. Increasing data demand requires efficient spectrum utilization. Number three is power efficiency. Uh, High power usage can be an issue for mobile and IoT applications. Four is multiwatt fading. Wireless signals reflect off buildings, mountains, and other obstacles, causing multiwatt fading. Wireless signals may experience interference due to reflections. And number five is synchronization issues. Advanced modulation schemes like QAM and PSK require a precise synchronization between transmitter and receiver. Now I will discuss what are the future trends in modulation techniques. Number one is 5G and beyond. New modulation techniques like OFDM means orthogonal frequency division multiplexing and massive MIMO are enabling in ultra-fast 5G networks. Future 6G technologies may use terahertz frequency bands for even higher data rates. Number two is AI and machine learning in modulation. AI-driven modulation techniques optimize signal transmission, uh, reducing errors and improving efficiency. Number three is quantum communication, secure data transmission through quantum-based techniques. Number four is software-defined radios, SDR. SDR technology allows dynamic switching between modulation techniques, improving adaptability in wireless systems used in military, satellite, and next generation IoT applications. Number five is energy efficient modulation for IoT. Low power modulation techniques like long range and narrowband IoT enable long range communication with minimal energy consumption, essential for IoT, smart cities, and healthcare applications and industrial automation. So, in conclusion, modulation is a fundamental aspect of communication that enables efficient and reliable data transmission from AM and FM radio to satellite and 5G networks. Modulation techniques continue to evolve to meet modern demands. Future advancements, including AI-driven modulation and quantum communication, promise to revolutionize the field. Thank you everyone for your time.